Let's dive into a concept that could literally reshape how our computers work from the inside out. We're going to talk about a problem that's been slowing all of us down for years, a massive bottleneck that's been hiding in plain sight. This quote just nails it. For decades, the answer to making computers faster seemed simple, right? Just build a faster processor. But we've slammed into a wall. The speed of your CPU, it turns out, isn't the only thing that matters. And today, it's not even the main problem anymore. So if it's not the processor, what is it? What's really holding things back? Well, let's pull back the curtain and look at the real bottleneck, the hidden wall that almost every modern computer has smacked right into. Turns out we're up against three modern villains. First up, you've got memory latency. That's the tiny but absolutely critical delay that happens every single time your computer needs to grab a piece of data. Then there's heat generation. Our memory gets hot, really hot, and that forces the whole system to throttle down just to cool off. And finally, system endurance. Constantly reading and writing data literally wears out the physical parts over time. These three things, they're the real culprits. But every big problem inspires some really creative, out-of-the-box thinking. And that brings us to a radical new solution. So let's meet Hypercache, an architecture that's been designed specifically to take on those three villains head-on. So what in the world is it? Okay, think of Hypercache as a totally new way of handling data on the fly. It's this really clever mix of magnetic storage and pathways that use light, which lets it completely sidestep the physical limits of our current memory. Magnetic memory and optical paths? I know, it sounds a little like science fiction, doesn't it? So how on earth do these two components actually work together to create something so fast? Okay, so here's the magic behind it. It takes the stability of magnetic memory, which is great because it holds onto data without needing constant power, and pairs it with the mind-blowing speed of optical paths, which move information using light. That combination of rock-solid stability and pure speed, that's the secret sauce. So what does this actually look like in the real world? Well, if you look at our standard memory, our DRAM, it's constantly refreshing itself, which generates a ton of heat. Hypercache, on the other hand, just delivers stable performance with way less heat. And check out this last point. While traditional systems really start to choke and stall under a heavy, continuous workload, Hypercache is literally built to thrive in those exact conditions. Okay, so does this just kick our old memory to the curb? Nope. And this is really important to understand. Hypercache isn't a replacement. It's a completely new layer in the system. It's an addition. Probably the best way to think about it is as a vital bridge. It's a bridge that spans the enormous performance canyon that's opened up between our lightning-fast processors and our, frankly, much slower main memory. So here's how the new pecking order works. When the CPU screams for data, it doesn't have to go all the way to the slow RAM anymore. Instead, it first hits this ultra-fast hypercache. This new layer basically acts like a shock absorber for all those constant high-frequency requests, which means the main memory gets bothered way less often. And the result? A massive, massive drop in latency. This is exactly why this isn't just some clever little optimization. It's a fundamental architectural shift. We're not just tweaking a part or making one component a little faster. We are changing the entire blueprint for how computers manage data. We're decoupling that need for speed from the old physical chains of heat and wear and tear. So why does all of this matter so much right now? Well, because the demands we're putting on our systems are just exploding. We're at a crossroads, and it leaves us with a pretty stark choice. We either figure out how to scale, or we're going to stall. I mean, just think about the most demanding things we're doing today. We're talking about AI, real-time data analytics, and edge computing. These are all fields that are crunching unbelievable amounts of data, where every single millisecond counts. And these are precisely the kinds of jobs that break our current memory systems, and they're the ones that stand to gain the most from this new architecture. So as these massive data-heavy workloads just become the new normal, the way we design our memory is going to define what's even possible. The question isn't just about speed anymore. It's about whether our systems can actually keep up and continue to scale, or if they're finally going to hit a wall and stall under all that pressure.